Let's get started. So this week today we're continuing our conversation about testing. On Monday we didn't introduce testing. We started testing different ways, and we showed three kind of techniques to help you do your testing. We saw testing with a hash map to keep your test cases organized by storing the inputs and expected outputs in the map and then iterating over the map to test your values. And we saw testing, a method that takes multiple inputs, and how it helped to create a test class for your test cases, then create objects of that type to be able to get all of your test cases organized for those applications. And then finally, we saw testing array lists, which is the most directly impactful for your homework. Testing two lists by going index by index and making sure the lists contain the same value at the same index. We're going to continue that conversation with how to test linked lists. And before we do that, I want to go through the homework task 4. Just kind of talk about what is in this thing, what we're asked to do for homework 4. So I guess I'll just start right from the top. For the structure, you're sticking with the same project. For all 9 programming tasks, the intent is that you'll continue, and I think we'll reach this goal, is to just keep building on the same project and keep expanding more functionality, more classes in the same project. So you have all of your code for the 9 programming tasks in the same project. For the application objective tasks, that'll probably change. You'll have different projects for that. This is a testing-only class. I know at least somebody in the class is going to write all the code for these, not knowing they were only supposed to write the test, so I want to say this as many times as I can. I said it a lot on Monday, but you're only writing the tests for the next 2 tasks of the class, of the course. So first, we're writing the test for task 5. We're writing the test for task 5. For this, we're going to include a Bayesian average rating method in our song class. So far, we've already computed the average rating. We're doing average rating. Hopefully, you've all done average rating by now, at least for... no, that's not necessarily true. We did average of an array list in task 1, but not necessarily ratings. But anyway, you'll have the average rating of a linked list, where you just straight up compute the mathematical average of the ratings. And this has some problems in the real world. So there's a lot of explanation for this task. Most of it's just explaining what Bayesian average is and why we use it. So I want to highlight that. If we have songs out there, we have a song, way to rate songs. Everybody's rating songs and having a good time. And we have a song that has 10,000 ratings with an average rating of 4.9. I hope we all would agree that that's a pretty good song. Like, that's a song you probably want to at least check out. Maybe it won't be your style or whatever, but it's a song that you're at least going to check out. And then there's another song that has an average rating of 5 out of 5, a perfect song with only 1 rating. Only 1 person reviewed that song and gave it a 5 out of 5. Is that song better than the 4.9 with 10,000 ratings? I think we can all agree that probably not. I mean, maybe it's just the greatest song of all time and only 1 person has heard it so far. But more likely than not, we have a lot of uncertainty here in that song probably isn't that great, just the first person who rated it really liked it. So we want some way to be able to compare anything that we rate, really, like comparing products on Amazon. Amazon doesn't just give you all the 1 rating of 5.0 items at the top of your search. So we need a way to compare things and factor in this uncertainty. And one way to do that, one solution, is Bayesian average. So now instead of just straight up computing the average, we're going to simulate some fake ratings into that computation. For a lot of the homework, I like to stick with 2 ratings of 3. Tends to give us pretty good results. But your method is going to take 2 ints, which is going to be the number of extra ratings and the value of those extra ratings. So if we add 2 extra ratings of value 3, now that song that had 1 person rate it of 5 out of 5, now the Bayesian average of that song is going to be 3.67, which is more accurate after factoring in our uncertainty of, we don't know. Like, that's probably how you're going to treat that song. It's roughly a 3.5 or a 3 or something, because you don't really know if it's going to be a great song. But the song with 10,000 reviews and an average of 4.9, it won't even notice those 2 extra ratings of 3 added to it. So this is a way that we kind of punish, not necessarily punish, but adjust anything that has very few reviews by saying you have to have enough reviews to kind of overcome those fake ratings before we can start trusting your actual rating. And the same is true in the other way. Why it was a mistake to say the word punish. Say one person reviewed a song a 1 out of 5. Well, now those 2 3s are going to increase that to say, hey, we're not so sure we're ready to call this song complete trash yet. Let's get these 3 ratings of 3 actually increasing the rating before we say that this is the worst song of all time, an absolute perfectly bad song. We don't want to say that. But once you get a lot of bad ratings, then it's going to be a bad song. So Bayesian average gives us a way to be able to identify all that, get that more useful information out of our averages, and then we can sort by Bayesian average to actually get the best songs at the top of the list, at the top of the charts, I guess. So that's what we want to set up is Bayesian average of songs. So now instead of going through your linked list and just computing average, you'll add these extra ratings, compute the math to add those extra ratings, and then compute the average. And any numbers are valid for these, I guess, except I probably should have added something here of what the numbers should do if they're negative, the take away ratings. But negatives, I would say, would be invalid inputs here. I should have added a line just to make sure we cover that edge case. But 0 is a valid number for extra ratings. If you say, give me 0 extra ratings, no matter what the second argument is, second parameter here is, you're just going to return the straight-up average, the regular average. You can just call your other average method and return that. But once you add extra ratings, it's going to be some extra math. Remember, we're not implementing this, not implementing the method for task 4. You're just writing the test. So to write the test, it's math. If I added 2 ratings of 3, for example, if that's probably your first test case you should write, if I'm adding 2 ratings of 3 to this list, what's going to be my actual average? You get a calculator, you punch in, well, probably a calculator on your phone or laptop these days. You punch in the numbers, you do the math, and then have that as your test case. So you're just punching in numbers and hard-coding the expected values for these test cases. You're not implementing Bayesian average yet. Implementing Bayesian average, again, I can't say this enough. If you start implementing these methods, the size of task 4 would blow up tremendously. You'd be doing 3 tasks in 1 week. Don't put yourself under that. Just write the test cases for this. And then we're going to add a movie class. To start, it's going to be a constructor that takes a string, which is the title of the movie, and an array list of strings, which will be all of the cast of that movie. We want to know who's starring in this movie in an array list of strings. And then we're going to have getters for both of those values. My eyes. Get title and get cast, which honestly for those, you might as well implement those methods because, hell, as we saw last time, IntelliJ will generate those for you with all the right capitalization and everything because I'm using the standard get cast, get title. You name your instance variables title and cast. You can auto-generate that code. So there's no harm in creating the constructor and get title and get cast. Get cast, there is some trick here to the testing. So when we give the cast in the constructor and then call get cast, we're going to get the same exact names as we gave to the constructor in the same order. So we can go index by index through our array list to check those strings, but getCast can return the names with different capitalization. And it can be different capitalization for any character in these strings. So you might get the list with just all of the right names. You might get the list with all the names in all lowercase, or you may get some crazy mix of upper and lowercase. So when you're comparing the strings, you make sure that you ignore the case of those strings. So if a character is upper or lowercase, doesn't matter, accept it. Accept it as the same string if it's the same characters. Don't worry, the string class has you covered here. Equals ignore case is going to tell you if two strings are equal while ignoring case. So you don't have to do any go through the strings character by character and compare. If it's a T, check if it's capital T or lowercase. Just call equals ignore case, and you can get rid of that. But you do have to go through the indices like we did last time, the last example on Monday. That's what you're expected to do here when you're testing get cast. Go through them index by index and call equals ignore case on the values of both lists at each index. And then add rating and Bayesian average. These are the same exact functionality as in your song class. So for this, you're expected to use your song testing, use the same thing for movie, and then you got both of them done. So no extra work on this one. Just using those test cases that you wrote for song, also using them for movie. And we have a few comparators. I don't want to talk too much about, you know what, why not? Because I might as well just go through this whole thing. I skipped over these in the last lecture, and I ended up coming back and talking about them a bit, so let's just do it. Song title comparator and song Bayesian rating comparator. Both of these comparators, you've talked about comparators in 115, so you should be familiar with the concept of a comparator, but just to kind of recap, and these are a little bit different than the ones you saw in 115. These comparators are going to take two song references to song objects and then return true if the first song should come first and false otherwise, including ties. So if the first song for song title comparator comes before the other song, what we call lexigraphically, but alphabetically, while ignoring case, then that song should come first and you should return true. If it comes, if they are the same or the first song should come after the second song in a full sorted order, then return false. And I have some examples of what, some edge cases that you should write tests for. Song Bayesian rating comparator, same idea, but it returns true if the first song has a higher Bayesian average than the second song and false otherwise. So using the song title comparator, we would want to sort alphabetically by song title. In song Bayesian rating comparator, we want to sort by Bayesian average rating in descending order. So we want the best songs first. If we're generating a playlist and we use this comparator, we want the best songs first, and then the songs progressively get, not necessarily worse, but lower Bayesian average rating. There's some syntax you'll need that we haven't covered yet, so I just straight up gave you the code on this. If you already started Task 4 and you haven't looked at the doc in a while, I did add this yesterday, I think. So for the song title comparator, the song Bayesian rating comparator, and this generic comparator, you should create these three classes in your code and just paste this code. This is all you need for Task 4, and then everything else is in your tests. You'll write tests for these comparators. But you can leave these stubbed out as return false. That's perfectly fine. But this is the syntax. We haven't talked about what this extends means yet. That's next week's content. It's inheritance, but I can't ask you to do Task 4 relying on Task 5 content. Doesn't work like that. So I'll just give you the code. You don't have to understand what extends means. Just paste this and test song title comparator and song Bayesian rating comparator as though this extends comparator of song didn't exist. At least for now. And then next week, we'll talk all about that syntax for an entire week. You'll love it. It's going to be great. And then finally, the stuff that we want to talk about today. So all of that stuff you could test right now. You have everything in your tool belt, namely after the third example on Monday, where we compared two array lists. That's the last thing that you need to test all those. And I'd argue that you don't even really need that. Like, you could have come up with that on your own. This whole week is basically like tips and tricks. But the last tip and or trick that we're going to show is how to compare two linked lists, which is how you're going to test the Task 6 functionality in Test Data Structures 2. For this, we're going to create a playlist class. We're actually going to use those comparators that we wrote and actually sort songs by Bayesian average rating and by title. Again, you don't have to implement the playlist functionality yet. We're gonna use a tree for it. It's going to be ballin'. And you're going to use this playlist class, add songs to it, and get song list. Get song list is going to return a linked list of songs, specifically a linked list node of songs, representing the head of the list of the head node of the list, and it's going to be in sorted order according to a comparator that you gave to the playlist constructor. So you have the task of checking if that returned list is in sorted order according to either the title, if you gave it a title comparator, or decreasing Bayesian average rating if you gave it the Bayesian average comparator. So we have the need to test a linked list and see if it has the right values in the right order, and that's what we want to talk about for all of today. So any questions on this before we get started? And I'll give I think I forgot to give this disclaimer in this lecture on Monday, but whenever I'm going into IntelliJ, which we'll spend the rest of the time in IntelliJ, and doing open-ended, just coding and doing examples, I'm fine getting off track and having it as a freestyle lecture. If there's something that you're struggling with, especially on the homework or something, and it's at least semi-related to what I'm doing, just let me know. I can veer off track a little, and we can freestyle this a bit. As opposed to when I'm doing slides, like I'm going slide to slide to slide. I'm just on rails on a slides lecture. But when it's IntelliJ, so open-ended, it's freestyle. I can go wherever we need to go. As long as I cover comparing two linked lists, which there's enough flex time in there that I can get off track a little bit. So with all of that, any questions? Rarely do students take me up on that offer. I'm waiting for, every once in a while they do, but I'm waiting for that to happen more often, where students get me off track on these lectures. You'll write, so the question is, how do we test the methods if we didn't write them? So you'll, what we call stub them out. So, hey, I do get to get off track. Yeah, I'm excited. Thank you. So, for example, I wrote tests. Let me just comment all of these in. So this is that was the wrong button. So this is the homework code where I wrote a lot of tests for methods that don't exist. And as these methods and classes start existing, as you start typing them, you'll uncomment the tests and start working on them. The idea is that you'll write your tests. Nothing's imported. Everything's going to be errors all over the place because nothing exists. But let me delete this. So first, we want to test the rating class. That's just the first one that I saw when I popped in here. We want to test the rating class when it doesn't exist. So let's say for this, it was the same thing as task 4. Write a class, test a class named rating that should have the rating stuff. It's going to be a bad example because writing a stubbed out rating is basically writing rating. But I'm going to create the class. And I'm going to create just the methods that I need for this class. So this class should have a constructor that's going to take, it's int first, right? Int. I'm going to check just to make sure I don't mess this up because somebody's going to, I was going to do it backwards too. Reviewer ID and then rating. So this takes a string and an int. And I'm just going to leave that blank. This doesn't have to this returns an object, a reference to an object, the object that's created. But it does that automatically for me, so I don't have to add any code here. And then it's going to have public string. Song would have been a better example for this, but I'm too far down. Reviewer ID, 2 capitals, I believe. But just like last time, I'm going to cut and paste to make sure I get the... Oh, I want to be in test classes, actually. I'm in the wrong thing. Actually, we can do this whole thing. Let's do this whole thing. Reviewer ID, I did get the right naming. So to get reviewer ID, And what I'm going to do, instead of implementing the methods, this is not the best example because it's just a getter, but I don't have to create my instance variables here because I'm not implementing any functionality. And I'm going to stub this out. As long as I have the right input parameters and parameter types and the right return value and the right method name, which we call the method signature, as long as I have all that right, I don't care about anything else because I'm not actually implementing the code. So I'm just going to return some default value. For a string, I'm going to return empty string, public int, get rating. Again, int, not in an integer. Return 0. Public set rating, int x, void. In public, void, set reviewer ID. That takes a string. So I'm not actually implementing those methods right now. I'm just going to stub them out, which means they do the minimum possible. They're not actually doing anything. Reviewer ID just returns empty string, rating returns 0. These methods that return void, I don't have to implement anything. I don't do anything at all. But when I go back to my test compiles, and I can run it to make sure that everything is working the way that it should, at least hopefully, unless I name something the wrong way. And then it's going to fail. Well, I'm not even going to think about that error, but good thing we don't have to run this today. But we would run that and then see if it compiles. As long as it compiles and runs, and then the very first assert should fail because the code doesn't do anything. And then once you have everything set up, and you carefully wrote out some test cases, thoughtful test cases, and for things like Bayesian average rating, you're not actually doing, it's going to sound bad, but you're not actually doing computer science. You are because you're testing and doing things. But you're not like writing complex algorithms or anything. You're doing straight up math. You're going to get your calculator and punch in the numbers and compute what the expected value is and hard code that into your test. So there shouldn't, I know there's going to be issues, but there shouldn't be anything that goes wrong there. If you made it here, I expect you can add numbers and divide. I know little mistakes happen, but that's at that point, you can submit to Autolab once you have your test cases. Then Autolab will point out if you do have any mistakes with that. But it's math to compute your test cases, comparing strings in alphabetical order. All I really asked you to do, right? There's not too much very complex there. That you should be able to do those without having the actual code to verify your test. You shouldn't have the code to verify your test. You should be writing your tests first and embracing test-driven development as, I shouldn't say should, but it's a very useful strategy. Did that answer your question, Elise? Okay. Where can we find the tests we made in class as in lecture? So the tests that like the test I did on Monday, I didn't push the tests that I made on Monday to any repo. They were very similar to the ones in the examples repo. Today I'm going to deviate a little bit more from the examples repo, but they will still be fairly similar. I'll say the code will exist in the lecture videos, but they won't exist anywhere outside of that. The issue is that I'm doing live demos in 3 different lectures. It looks different in each of the lectures. Paul has 2 separate repos for both of his lectures, and he pushes to both of them separately. And I don't know, I just don't. I just don't see the need to do that since they're very similar to what's in the core repo. But you can always watch the videos and type them down. So with that, let's get to testing a linked list. So we want to test a linked list. So the first thing we're going to do is create a linked list. And actually, there's one more thing I want to say while we're in the project repo, because I've been getting this question quite a bit. The project repo, the handout that you have that you cloned for way back in task 1, it always had this linked list node class in it which is the same linked list node from the repo, you have all these methods available to you for free. All the methods we talked about in lecture are in here. They're right there ready for you to use. And you do have to use this class. I see quite a few of you, when we say linked list, you just flat out type linked list. We talked about this for a whole week, that linked lists are actually linked list nodes. That it's nodes linked together, and that creates the list. So when we say linked list, we actually mean this linked list node. And you do have to use the linked list node class that's provided in the repo. So when something takes a linked list node or returns a linked list node, it has to be this linked list node, an object of this type. You can't use, because Java does have a built-in linked list that some of y'all are tempted to use, either by accident or otherwise. That's not the right one. It's going to cause all kinds of errors in Autolab. The whole idea of these lectures in this task, task 3 and task 4, is to get you comfortable with a linked list. How to use a linked list, getting your hands on the actual nodes and figuring out how these things work, the science behind how it works. And then outside of any course where you're learning exactly how a linked list node works, which will be 116 and 250, you'll revisit linked list nodes. Outside of that, yeah, just use the built-in class. Like, who cares? Do whatever's easiest. But while we're learning how a linked list works, you're using the linked list node class to understand how linked list nodes actually form a linked list. So please use that class. It's the same class that I'm going to use right over here. We have this linked list node class, and we implemented some methods: size, toString, find, and append. So let's test these methods, specifically append, toString, and append and toString. I thought there was a third one. So those are the only ones I'm going to test. So before we get into that, we have to create a linked list by creating a linked list node. So when I create a linked list, I have to create a linked list of something, just like array. This has been a surprisingly common office hour question too. You have to create a linked list node of something. When you create an array list, you don't just say array list equals new array list. You don't do that. You create an array list of something using your generics. We give it a type and say, this is the type that my linked list stores. So if I say, give me a linked list of songs, you'll create a linked list of songs using this syntax. For this example, I'm going to create a linked list of strings. And a linked list is just a reference to the first node in a linked list. To represent an empty linked list, this is also a common question, but this one I more expect because you're new to linked lists on this one. That syntax we've been seeing since Monday of week 2, so I was surprised to get that question so often. But a linked list, if we want to represent an empty linked list, if a linked list is just a reference to the first node of the linked list, it's hard to represent an empty linked list. And the way we do represent an empty linked list with the setup that we have is by setting it equal to null. Now, if you use like Java's built-in linked list, it actually is a wrapper class for the linked list node, meaning it has an instance variable for the head of the list, and it'll store null in that instance variable if the list is empty, much like our stack and queue did. We had a reference to null, but we had it wrapped inside another class, so it was a little bit hidden from us. But in general, to represent an empty linked list, this is an empty linked list. It just straight up equals null. And then all throughout our code, when we're working with linked lists, we're going to have if the thing is null, if the thing is null, if the thing is null, if the node is null. We're going to do one thing if we have an empty list. You're calculating the average of linked lists of doubles. You're going to say if the list is null, return 0.0, else there is something in this list, we're going to return something else. So this is an empty linked list. And then let's put stuff in it. So let's create the first node just so we have something to start with when we create our first node. What should we store in this? We didn't come up with anything interesting in the last lecture. What should we store as strings in this thing? I'm never good at coming up with examples on the fly to make them flavorful. What? What's it? Wait, what? Colors. Okay, I heard the wrong thing one of those times. Like he did just say that. Colors was the answer. All right, red and null. This is going to create a linked list of size 1. with just the value red. One thing I did see in office hours once was trying to create an empty list by doing this, which is a reasonable thing to try. It's not going to work, but it is a reasonable thing to try. This is not a linked list. This is not an empty list. This is a linked list of size 1. It has one node, and the value at that node is null. So we have a linked list of size 1 with the value null. That's very different than having an empty linked list. It's a subtle difference, but it is a big difference, big important difference. This is a linked list of size 1 with the value red. And then now that we have a node, we can start calling the node methods. And I'm going to test the append method and make sure append is doing what we want it to. Because, it might not be. Let's append green, blue. Oh, let me only do 4 because I don't feel like doing too much typing. And violet. So now at this point, we expect a linked list with the value, let me go step by step. We expect a linked list with the value red. And then we're appending. Appending is going to add to the end of the linked list. So after we append green, we expect the value red with a reference to a node with the value green. After appending blue, we expect blue to be at the end. Oops, I didn't grab blue. And then after appending violet, we expect violet to be at the end. So we expect our linked list actual to be a reference to a linked list node with the value red, with a next being a reference to a linked list node with the value green. Its next will be a linked list node with the value blue. Its next will be a linked list node with the value violet. So that's what we expect our end list to be. It's size 4, and it has these 4 values in this order. Order does matter. It's a sequential data structure, so order matters. And now we can start. Actually, before we do that, let's run this test. Does this test pass or fail? Passes. I haven't seen this yet this semester, but it is a common thing that happens every once in a while. This test passes. There's no assert that fails because there's no asserts at all. If you don't have any asserts at all in your test, it's a passing test because it didn't fail. No test cases failed. 0 out of 0 passing. So that's a passing test. So if you forget to have any asserts, which it happens every once in a while, it's fine. But if you don't have any asserts, every single time in Autolab, passed on a correct solution, also passed every incorrect solution, because your test literally just passes anything ever at all. So make sure you have some asserts in your testing. So let's assert some things. Assert, hit cap lock. Assert equals 4. This is driving me insane. I don't want all this stuff covering up my stuff that I'm doing. Actual dot size. So if I call size on this list, I would expect 4 to be returned. We can run this. Unless I made a pretty blatant error here, this should pass. And we can verify that at least the size is what we expect. And we're always going to hard code like this. When we're in test cases, this is one instance where we do hard code things. I mean, for completeness, for really accurateness. What am I saying? For the best code, you would say expected size equals 4. But you are still hard coding the values. You're manually verifying what do I expect, and then putting a number and then asserting that you got that number. All right. But then the big show. Okay, size, that's fine. But we want to check if this list contains all the values we expect in the appropriate order. For this, I like to create the linked list that I'm expecting, and then using a helper method to find out if I have the same list in both places. So I'm going to create a second linked list of string expected equals new linked list node of violet null. And I'm going to create this one backwards because It's just easier to prepend than append. And I'm manually creating this thing for test case purposes, so I can create it however the hell I want, as long as it is the right list in the end. So I'm going to create this with Violet, and I'm going to prepend the same way we did the very first time we saw a linked list. Linked list node of blue with a next of expected. And at this point, my list is blue, violet. So expected is a linked list node with the value blue. So blue is at the head of the linked list. And its next is expected, which was violet before blue was added. Next, we're going to prepend green, the next previous one. Prepend, it goes on the front. And we started with red. So our linked list is red. We started with violet, prepended blue, prepended green, prepended red, and we get this list, which is exactly the list that we're expecting when we appended to the end of the list. So this list is exactly the list that we expect, as long as the append method is doing what it's supposed to be doing. Now, for your testing, you could use the append method, but since I'm writing this test to test the append method, I'm not going to use the method that I'm testing at the moment. So now, I want to write my helper method. We'll stick with the convention. We'll do equals and then whatever we're testing. Expected, actual. No, I called it list. No, I did call it actual. Oh, yeah, the method doesn't exist yet, obviously. Where can we find the tests we make in... that was a while ago. Could you use a append function in line 16 instead of what you have? Oh, yeah, and I answered that, just naturally going through. We can. I could, but the purpose of this test is to test the append method. But in your tests, by all means, use the append method. Because if I'm using append to build the list, and then this code would look identical to this code, and at that point, I'm not testing anything. I'm just testing if the method actual does the same thing each time it's called. So my test would always pass, even with broken append method. What cases would we not hard code the tests? I can't think of anything off the top of my head, and if it's impossible to hard code, that's the only case you wouldn't. Actually, I do have a case. If there are a lot of multiple answers, we're not going to run it actually it's something similar this semester, but finding a path between two tiles on a grid, and you have to return the shortest path between the two tiles. So you could go this way to find the next tile, you could go this way, you could zigzag over. There's a large number of correct solutions. That's one case where you can't just say hard code, this is the answer, where you do actually have to have some logic to check the returned path to make sure it is a valid path and it's of minimum length. So that's one case you couldn't just say, the answer's 5 or the answer's this path and then go through the two paths and make sure they're the same. That would be one case where you're not hard coding. Yeah, so prepending and appending. Prepending means add it to the beginning of the list, and append means add it to the end of the list. So effectively, just the way that I built this, I ended up prepending to the beginning of the list. All right, let's write equals lists before we run out of time. We had that time. We'll be fine, but I just want to make sure. Equals, whoa. Public void, I need my return type. Because IntelliJ is pretty smart, if you haven't been convinced of that yet. I was trying to use the shortcut of telling me the name. It says, hey, you used a method name down here that doesn't exist yet. So as soon as I type E, it's like, oh, you're finally implementing that method. But I didn't type void, so it wasn't expecting a method name yet. So I'm going to write equals list. And this is where I am going to deviate a bit from what's in the repo. I'm going to hard code the type in this method to be the type that I am testing. So I'm testing linked lists of strings, whereas the repo, which I got to talk to Paul about this, I forgot we did this. The repo method takes a generic and then compares lists generically. But when you test things generically like that, you can only ever use equals and toString and a couple other methods. We don't want to work with generics. We want to actually test these strings. Or in the homework code that we saw, testing ratings, linked lists of ratings. And in the code that you'll write, testing linked lists of songs. We can't use generics for any of that. So expected. I might just update the repo, to be honest. Maybe that is where you can find the testing code for today, after I gave that long explanation earlier. Actual. And we want to check if these two lists are the same. So when this is first called, it's going to be on the heads of the list, but we're going to end up making this a recursive method that's going to navigate through all the lists, one node at a time. It's very similar to what we did last time when we iterated through two arrays by index and compared the values at each index, one index at a time. But it's a linked list, so there's a few extra things that we have to do. So, I mentioned whenever we're working with linked lists, we're going to have null checks all over the place. So let's start off with our null check. If expected equals null. So if expected equals null, that means we expect to be at the end of the expected list, or that the list is just straight up empty. Maybe we expect the list to be empty that was returned. So if expected is null, we're going to expect actual to also be null, and we're going to do that with an assert. I said we were going to stick with assert true all semester, but then we broke open assert equals on Monday. Since that opened up the floodgates, let's just go whole hog on this thing. We're going to use all kinds of asserts since we already started down that road. I'm going to use assert null on actual, and this is going to check, as the name implies, it's going to make sure that actual is null. So if expected is null, I expect actual to also be null. So I'm going to assert that to make sure that it's null. Otherwise, we got some checks to do. So if expected isn't null, then I expect actual to not be null. Now, if I just start doing actual dot, I'm going to get in trouble with this one because actual might be null at this point still. As soon as we do dot on null, we get a null pointer exception. So if I do actual dot and actual happens to be null, dot means your reference, take me to the object to which you refer. But if we ask null, hey, take me to the object to which you refer, null's going to be like, I don't know, I don't do that. I don't do anything. And it's a null pointer exception. So we have to be careful about this. We always got to check our nulls, especially with linked lists when we got nulls flying all over the place. So we're going to assert not null, actual. We're testing, so we're going to assert, make sure that it's not null. And if we get to this line of code, line 18 right here, if we get to this line of code, we know we're good in terms of nulls because this had to have been false to get us into the else block, and we just asserted that actual is not null. And once an assert fails, the entire test shuts down, the program ends, everything's over at that point. So if this is false, meaning actual is null, everything shuts down right here and the test ends. So if we made it to the next line, we know that expected and actual are both not null. And now we're free to use our dot operators, head over to the heap, and check out those objects that we have. Because we know we don't have references to null. That means we have references to objects on the heap of the type of these variables, which is linked list node of string. And we can do our assert. Assert equals expected.value. Dang, that's killing me. I got to disable that. Actual dot get value. If I could type. So we want to assert that the two values at this node are equal. So if this is the head of the list, we're going to say, we're going to check, do we expect empty list or not? If we don't expect empty list, make sure actual isn't the empty list. And then make sure the first value of each list is the same. And then we're going to do it over again. We're going to move on to the second node in each list. and keep going through each node one at a time while comparing their values. And to do that, we're going to make the recursive call equals list expected dot next. Oops. This is Java. So we get next actual dot get next. So we're going to recursively call this on the next node, and this is the beauty of linked lists. It's all just nodes. So if it works for the head of the list, it works for the next element of the list, the next nodes of the list. It'll work for nodes in the middle of the list. It'll work for the last nodes of the list. And it also works for null. This method does it all. It does the null checks and then moves on to the next ones. So we're done. We just compared two lists. We can run this code. I would expect it to pass. But I always like to see my test fail. So I'm going to change something here, run it, and make sure I actually am doing the checks that I expect to run. So violet with a capital T is not the same as violet, and I did assert equals on them, so I do expect this to fail. Since I'm using assert equals, I do get a little information here. And I also get the stack trace. When you see these error messages, you click on the top one, that's the line that had the error, the comparison error here. But you can also see all the stack frames. We can see that this method was called here, which called the method in the next stack frame, which created a stack frame, which created a stack frame, which created a stack frame, which had an error. But in your homework, we don't care about case. We want to ignore that capitalization error here. To do that, I mentioned this method, expected.getValue.equals ignore case. Let's just ignore all those cases. Now, no matter what the upper and lower case is, it's all going to be ignored. And we're just going to assert that the strings are the same regardless of case. And we do get our test passing, even with that capital T on violet. And I'm going to get this in. There's one more thing I want to show. We did something very similar, or in the homework, you have something very similar in the given tests for task 3. Except you have to do a little bit more. When you're comparing the lists, the values, you're comparing ratings. So we have another helper method to compare a rating, 2 ratings, to make sure the rating's the same and the reviewer ID is the same. Other than that, this is the same exact method that we just built. This is the one that's given to you in the homework handout. Same idea, same concept. And this is more similar to what you'll do in task 4. You'll compare 2 linked list nodes of songs, and it's helpful to write that helper method that takes 2 songs and compares them.